To find the area bounded by the two functions f of x and g of x, so that's going to be all of this stuff here, I'm going to first note that the red function is f of x because it's linear, and then the blue function is going to be g of x because it's a quadratic. And notice that the function g of x is always greater than the function f of x when the area is bounded. So to find the area between the two curves, we're going to use this following fact. If you take the difference of the two functions, the larger minus the smaller, and you integrate it from where it's bounded, that's going to be the area A that we're looking for. So to solve this problem, I'm going to write the integral, put a parentheses. I'm going to take g of x, which is 6 minus x squared, and I'm going to subtract f of x. Now I got to be careful here. When you subtract a function, you have to distribute that negative. But there's something else I need to know too. I need to know, where does the area that's bounded start and where does it stop? I mean, I can read it right off the graph because I have it labeled here. It's going to go from -2 here to +1. If you didn't have a graph of this in front of you, the way you could figure this out is by setting f of x equal to g of x. F of x is equal to x plus 4. G of x is equal to 6 minus x squared. And we would solve this thing for x. I'm going to add x squared to both sides. And I'm also going to subtract 6, changing it to a quadratic that's equal to 0. I think this factors. Have an x and an x. It has to be a +2 and a -1. Okay, and this means the solutions are x is equal to -2 and x is equal to +1, which matches up with the picture that we have here and here. -2 and +1 are the two places where the functions are equal. To complete this problem, what we have to do is solve this integral. Maybe I'll simplify the inside a little bit before I find an antiderivative. So let's see, 6 minus x squared minus x minus 4. So this is the integral from -2 to 1 of, okay, if you do 6 minus 4, that's 2, minus x squared dx. So what we need now is an antiderivative for this. Once I figure out what that antiderivative is, I'll plug in 1, I'll plug in -2, I'll take the difference, and that will be equal to this area here. Okay, I'll start with finding an antiderivative of 2. I'm going to write this above here. I know it's going to be 2x, and the reason is the derivative of 2x is equal to 2. Okay, so now I have minus. I need an antiderivative of x. Well, it's got to be x squared over 2. And the reason is, when you take the derivative of this, the 2 comes down front, cancels with this 2 here. You would subtract 1 from the exponent, taking you back to just x. And then we have minus. Okay, we have to have, it's going to be x, it's got to be cubed over 3. And again, the reason is when I take the derivative of this thing, the 3 comes down front, cancels with this 3, subtracting 1 from this exponent gives me this here. This thing that I've written is the antiderivative. It's an antiderivative. My final answer is going to be f of 1 minus f of -2. I'm just going to get these values directly in a calculator, so I'm going to enter in the antiderivative. And plug in 1 and plug in -2. Okay. So let's see. All right, I'm going to do an approximate solution. It'll be close enough. F of 1 is about 1.17, and I'm subtracting f of 2 is, all right, that's -3.33. So that's 1.17. The negative is going to be plus 3.33. And when I add those two values together, I get 4.5. Now, that's an approximate value. It's going to be very close to the correct answer. You could easily simplify this to get the exact value, but I think that is good enough for this problem. So just to recap, you have to examine the function, and you have to determine what the bounded area is this, and we're talking about this piece here. You have to know what the larger and smaller function is. To find this area, you take that difference and you integrate it from the lower bound to the upper bound. We had to figure out what those two values were. I used a graph, but you could also solve an equation. The rest is just carefully simplifying. And once you have a simplified function, finding its antiderivative, plugging in the bounds, taking the difference to get our final answer. For question 2, we'd like to evaluate these definite integrals, and we're going to be using the fundamental theorem of calculus. So in part A, let's see, the function inside the integral is 2e to the x plus 8x cubed, and I'm going to write this as x to the 1/2. And we need to find an antiderivative. So that is something when you take its derivative, it brings you back to here. I'll go term by term, starting with 2e to the x. Well, the derivative of e to the x is e to the x, so I know it has to be e to the x, and put a 2 in front of it. I'm just going to think about this one. The derivative of this thing is, ignore the 2, take the derivative of e to the x, you get e to the x, but then you would just multiply this 2 back. Okay. For the next piece, we have plus. All right, we get, I'll leave the constant alone. Here we have x to a power, and the trick is you add 1 to the exponent and divide by that new number. The reason this works is when you take the derivative, the 4 would come down front, it would cancel with this 4, it would subtract 1 from the exponent, leaving this 8 alone, would take us back to this piece. And I'm going to use that same logic in this last expression. If I'm going to take the antiderivative of x to the 1/2, I'll add 1 to the exponent. So 1 plus 1/2 is 1.5, but I'll leave it as a fraction and call it 3/2. I now have to divide by 3/2. I'm going to simplify this. This is, okay, 2e to the x is good enough. 4 goes into 8 twice. And if I'm dividing by a fraction, I can multiply by its reciprocal. The fundamental theorem of calculus says that if you are going to calculate a definite integral and you have an antiderivative, you plug in the upper bound and subtract off what you get when you plug in the lower bound. Whatever that number is going to be the answer. I don't think it's going to be, again, some like nice whole number or something like that. If I put 1 into the antiderivative, I get 2e to the first. And then the next two terms are actually just both 0. If I put, oh, I'm sorry, that's not true. I'm putting 1 into this. So I lied. If I put 1 here, I am just left with 2. And if I put 1 here, I'm left with 2/3. And now I subtract off what I get when I put 0 into this expression. Well, if I put 0 here, e to the 0 is just 1, making this whole first thing 2. Okay, now if I put 0 in place of these two x's, they're both just 0. If I simplify all this, I get 2 times e to the first. I have a positive 2, and I'm going to subtract a 2, so those two things cancel, and I'm left with 2/3. So this is the exact value, and that would be the final answer. For part B, same idea. the function is f of x is equal to cosine of x minus secant squared x. And I want to find an antiderivative. Okay, well, the antiderivative of cosine is going to be sine. And the reason is the derivative of sine is cosine. Okay, minus secant squared. Can I think of a function whose derivative is secant squared? And this is one where we just have to refer to the rules that we developed earlier in the semester. We said that the derivative of tangent is in fact secant squared. So this is the antiderivative that I'm going to use. So again, nothing left to simplify. It's just a matter of putting in pi over 4, and then putting in 0, and taking the difference. Okay. Okay, so here we're going to have some exact values, but sine of pi over 4 is going to be the square root of 2 over 2. Minus, now tangent of pi over 4 is going to be 1. And now I subtract off what I get when I put 0 into both of these functions. And it's actually 0 for both sine and tangent. Altogether, this means that the final answer is the square root of 2 over 2 minus 1.